Let us verify Green's theorem. For the integral 3x squared minus 8y squared dx plus 4y minus 6x dy. So we want to verify Green's theorem for this integral, and when we say Green's theorem, we need a closed curve. In this case, closed curve is a curve formed by the intersection of those three lines, x equal to 0, y equal to 0, and x plus y equal to 1. In fact, those three lines will intersect to form a triangle. Let's draw a triangle. First of all, we have the line x equal to 0. That's y-axis. So let's draw the line x equal to 0. That's the y-axis. So we have drawn y-axis. Next, we have the line y equal to 0. That's x-axis. And we have drawn the line y equal to 0, and that's x-axis. Fine, we have drawn x equal to 0, y equal to 0. Now we need the line x plus y equal to 1. If we draw it, then we'll get a straight line. If we draw it, then we'll get a straight line, and we have a straight line. So we want to verify Green's theorem on a triangle OAB, and for the integral is given to us. Triangle is given to us and integral is also given to us. Let's write the exact formula for Green's theorem that we want to verify. The formula is integral over closed curve f1 dx plus f2 dy equal to integral over region del f2 del x minus del f1 del y dx dy or dy dx. That depends on preference. We prefer dy dx. Once again, we have by Green's theorem integral over closed curve f1 dx plus f2 dy equal to integral over region del f2 del x minus del f1 del y. Now further, we should make sure that we have a closed curve, and it's necessary that we have anti-clockwise direction for that closed curve. We need a closed curve, and not just a closed curve but a directional closed curve. So we have a closed curve OAB, and of course it's easier to evaluate integral over the region. Let's evaluate integral over the region first of all. So that means we will evaluate the right hand side, that is this integral over the region. Now we are told we are given a triangular region, so we want to integrate over this region. You see that we can cover this region. We can exactly cover this region if we change y from y equal to 0 to y equal to 1 minus x. That's because x plus y equal to 1. If we change y from y equal to 0 to y equal to 1 minus x, then we will be covering this region, no doubt about it. But not only that, we will be covering something more. This region also we can cover, and if you regard negatively, maybe we can cover this region also. So how do we remove those? Well, pretty simple. Since we don't want to go outside the triangle, so let's change x from x equal to 0 to x equal to 1. That's the point, x equal to 1. Yeah. So let's change x from x equal to 0 to x equal to 1. Then let's change y from y equal to 0 to y equal to 1 minus x. Then we will be exactly covering this region, the triangular region. Let's do it. So right hand side of Green's theorem is integral over region. In this case, region is our triangle OAB. Integral over triangle OAB. Integral over triangle OAB. Integral over triangle OAB. That's our right hand side. Del f2 del x minus del f1 del y del f2 del x minus del f1 del y dy dx. That's our triangular region. But what are f1 and f2? For that purpose, we should compare this left hand side with what's given to us. We are given just integral over closed curve 3x square minus 8y square dx plus 4y minus 6x dy. Let's write it down. Let's just write what we have in Green's theorem. Integral over closed curve f1 dx plus f2 dy. Naturally, we should take f1 equal to 3x square minus 8y square, f2 equal to 4y minus 6x. So we should take f1 equal to 3x square minus 8y square. Let's take that. Here, f1 equal to 3x square minus 8y square, 3x square minus 8y square, f2 equal to I suppose 8y minus 6x. Did I remember correctly? No. f1 is 3x square minus 8y square. f2 is 4y minus 6x. 3x square minus 8y square, 4y minus 6x. All right. f2 is 4y minus 6x. Then we should compute this quantity del f2 del x minus del f1 del y. Let's do it. This implies del f2 del x minus del f1 del y. Del f2 del x, that's the partial differentiation with respect to x of 4y minus 6x minus del f1 del y, that's partial differentiation with respect to y of 3x square minus 8y square. So, if we differentiate partially with respect to x, then we will obviously treat y to be a constant. So, del x of 4y is just 0. Del x of 4y is 0 because we are differentiating partially with respect to x. So, we'll treat y as a constant. Now, del x of x is 1. So, we are left out with minus 6 minus del y of 3x square. Again, we are differentiating partially with respect to y of x square, and so we'll treat x square to be a constant. So del y of 3x square is 0, and negative will make it positive. 8 is a constant. Del y of 8y square, and that means 8 is a constant, and del y of y square is just 2y. 8 into 2y. So we are left out with 16y minus 6. Okay, we are left out with 16y minus 6. Now we have the right hand side that is the integral over the triangle del f to del x minus del f on del y. So we have evaluated del f to del x minus del f on del y. Let's evaluate over the triangle. So integral over the triangle OAB del f to del x minus del f on del y, that turns out to be 16y minus 6. We want to evaluate with respect to y first and then with respect to x. As we have noted earlier, if you want to exactly cover the triangle, then we must change from y equal to y from y equal to 0 to y equal to 1 minus x, and x should change from x equal to 0 to x equal to 1. Let's do that. We must change y from y equal to 0 to y equal to 1 minus x, and then x from x equal to 0 to x equal to 1. Let's do that. So if you want to integrate over the triangle, if you want to cover exactly the triangle, we must change y from y equal to 0 to y equal to 1 minus x, y equal to 0 to 0, y equal to 0 to y equal to 1 minus x, and then x from x equal to 0 to x equal to 1. That will exactly cover the triangle OAB that we have observed earlier. The function 16 del f to del x minus del f on del y, that turns out to be 16y minus 6 dy dx as it is. Now it's pretty simple to integrate 16y minus 6. Integral of y with respect to y is y square by 2. And integral of constant 16 as it is. Integral of y with respect to y is y square by 2. Integral of minus 6 is minus 6y. And we need to change y from y equal to 0 to y equal to 1 minus x. Y equal to 0 to y equal to 1 minus x. We need to change it last from x equal to 0 to x equal to 1. Okay, we have already integrated with respect to y, so we need to write dy, we just need to write dx. Let's calculate that. Once again, we need to change x equal to 0 to x equal to 1. Let's put the upper limit. Upper limit we can cancel 16 and 2 to get 8. So 8, and upper limit the value of y is 1 minus x. So 1 minus x whole thing square minus 6, upper limit value of y is 1 minus x. Lower limit value of y is 0, and dx as it is. Let's simplify the expression. We have only one variable x, so we needn't write x is changing from 0 to 1. We'll just write 0 to 1, integral from 0 to 1. Integral from 0 to 1. 1 minus x whole thing square is 1 plus x square. 1 plus x square minus 2x, and then we have minus 6 plus 6x dx. That's equal to integral from 0 to 1, 8 plus 8x square minus 16x minus 6 plus 6x dx. That's equal to integral 0 to 1, 8x square minus 10x plus 2. That's pretty simple to calculate. Integral of 8x squared is 8 into integral of x squared is x cubed by 3. 10x, if you integrate, we have 10 into x squared by 2. 2 if you integrate 10 into x squared by 2. And if you integrate 2 with respect to x, you will get 2x. X is changing from 0 to 1. So that's equal to 8 by 3 minus 5 plus 2. That is equal to 8 by 3 minus 3, that is equal to minus 1 by 3. Alright, so we have computed Green's theorem, but we have just done right hand side. Let's do the left hand side. So we have computed the right hand side for the Green's theorem, and we will verify it only if it turns out that, and it should turn out that left hand side equal to right hand side. Left hand side consists of closed curve, and as we have said earlier, we need the direction to be anti-clockwise direction. So we have O to A, A to B, B to O. Let's evaluate the integral. Integral over closed curve. Now let's do the left hand side now. Integral over closed curve f1 dx plus f2 dy equal to integral over OA f1 dx plus f2 dy, let's not write it, plus integral over AB plus integral over BO. We are not writing f1 dx plus f2 dy, but we have that closed curve that consists of three parts, OA, AB and BO. Further, we remind you that we need the direction to be anti-clockwise direction when we are maintaining that. Otherwise, we will not get the right answer. So, case 1. Along OA. Let's look at the figure. What do we have along OA? Along OA, we have y equal to 0 and x is changing from x equal to 0 to x equal to 1. You need to change x from x equal to 0 to x equal to 1. Along OA, we have y equal to 0 and we need to change x from x equal to 0 to x equal to 1. Let's do it. Comma, y equal to 0, comma, x is changing from that, we need to write. So when y equal to 0, then dy equal to 0. So integral along OA, integral along OA. We need f1, so f1 is 3x squared minus 8y squared, fine. Integral along OA, f1 dx plus f2 dy. Y equal to 0, so dy equal to 0. Why is it changing again? Equal to, since dy equal to 0, so we need not calculate dy, we just need to calculate f1 dx, and x is changing from x equal to 0 to x equal to 1. f1 dx, f1 is 3x squared minus 8y squared. f1 is 3x squared minus 8y squared, f1 dx. Let's see. plus 0 because dy is 0. Did I copy f1 correctly? Let's see. f1 equal to 3x squared minus 8y squared. We copied correctly. So once again, y equal to 0. So this is just equal to, since y equal to 0, this is equal to integral from 0 to 1, 3x squared dx. And that is equal to x cubed by 3. Integral of x squared is x cubed by 3. 3 as it is. We can cancel 3 and 3 out. We need to change from x equal to 0 to 1, and that's equal to 1. So we are done along way. Now case 2. Case 2. We are moving from O to A and then from A to B along AB. Okay, let's look at the figure. What do we have along AB? Oh, we are moving from A. At the point A, we have first of all, along AB, y changing from, along AB, y equal to 1 minus x. The equation of line AB is y equal to 1 minus x, first point. Second point, what is the value of x changing? At A, x equal to 1. And at B, x equal to 0. So along AB, you are starting from x equal to 1 and you are going up to x equal to 0. And throughout the line AB, we have got y equal to 1 minus x. I repeat everything again. We are starting with x equal to 1 and we are going up to x equal to 0. And throughout AB, we have y equal to 1 minus x. So these 3 points are required. Throughout the line AB, we have got equation of line AB is y equal to 1 minus x. Equation of line AB is y equal to 1 minus x. Along AB, we have y equal to 1 minus x. And your x is changing from x equal to 1 to x equal to 0. So let's evaluate it. Along AB, integral along AB f1 dx plus f2 dy. Okay, we have y equal to 1 minus x, so dy equal to minus 1, and your x is changing from x equal to 1 to x equal to 0. So integral along AB, you first of all with respect to x, f1 dx. So x is changing from x equal to 1 to x equal to 1 to x equal to 0. What about f1? f1 is 3x square minus 8y square dx. Remember, we have y equal to 1 minus x plus f2 dy. What is f2? F2, where do we have f2? Let's recall. f2 equal to 4y minus 6x. f2 equal to 4y minus 6x. f2 is 4y minus 6x. We are evaluating with respect to y, but dy equal to minus 1 here. minus 1 dx. Sorry, I made a mistake here. That's wrong. Uh, that's wrong. dy by dx equal to minus 1. So dy equal to minus dx. Let's correct it. So once again, along AB, your x is changing from x equal to 1 to x equal to 0. dy equal to minus dx, and y equal to 1 minus x. That's point we should also note. Y equal to 1 minus x. Let's write it down and evaluate it. So this is equal to 1 to 0, 3x square, value of y equal to 1 minus x. 1 minus x whole thing square dx. Dx, why should I write again and again? So 3x square minus 8 into 1 minus x square. X is changing from 1 to 0, plus 4 into y. Y equal to 1 minus x minus 6x, but we need to multiply it throughout by minus 1. The whole expression needs to be multiplied by minus 1 dx. Okay, let's simplify this expression out, the big one. X is changing from 1 to 0 as it is. 3x square as it is. 8 into 1, 8. Minus 2x into minus 8 plus 16x. Minus 8 into x square minus 8 x square. Minus 4 into 1 minus 4. Minus 4 into minus x plus 4x. Minus 1 into minus 6x plus 6x. Okay, 3x square minus 8x square. We got it to be minus 5x square. And then this is equal to integral from 1 to 0. 3x square minus 8x square. We got it to be minus 5x square. Then we have 6x plus 4x is 10x. 10x plus 16x is 26x. Plus 26x. We are done with x square, we are done with x, and we are left out with minus 4 and minus 8. That's equal to minus 12 dx. Now this is equal to minus 5 into integral of x squared is x cubed by 3 plus 26 into integral of x is x squared by 2 minus 12x. We need to change x from 1 to 0. Upper limit, we wrote it 0 minus lower limit minus 5 by 3 plus 13 minus 12. Upper limit is 0, lower limit x equal to 1, so we have minus 5 by 3, and x equal to 1, 13, x equal to 1 minus 12. Yeah, we did it correctly. That's equal to minus of minus 5 by 3 plus 1, that is plus 2 by 3. Sorry, minus of minus 2 by 3. Yeah, so it is plus 2 by 3. Yeah. Last case. bit simple. Case 3, we have, let's look at the triangle once again. We have traversed from O to A, and then we have traversed from O to A, and then from A to B, and lastly we should return from B to O to make a complete closed curve, and that's in anti-clockwise direction. So along BO, we have got x equal to 0, and we need to change y from y equal to 1 to y equal to 0. Alright, pretty simple case. X equal to 0 and y changing from y equal to 1 to y equal to 0. Let's do it. Case 3, we need to return from B back to O along BO. Along BO we have x equal to 0, y changing from y equal to 1 to y equal to 0. So integral along BO f1 dx plus f2 dy equal to, we have got x equal to 0, so we should observe that dx equal to 0. That will simplify our case. f1 dx is 0, so we are just left out with f2 dy, and y changing from y equal to 1 to y equal to 0. f2, what is our f2? f2 is somewhere where we have f2 is 4y minus 6x. We have f2 equal to 4y minus 6x. f2 equal to 4y minus 6x. But along BO we have got x equal to 0, so this is just integral from 1 to 0, 4y dy equal to 4 into y square by 2, 1 to 0, and that is equal to, when you write upper limit 0, we have 0. When we write lower limit, we have minus 2. That's minus 2. Well, then we have computed integral along. We have computed integral along OA, and that's turned out to be 1. Along OA, we got the integral equal to 1. And along AB, we got the integral equal to 2 by 3. Integral equal to 2 by 3 and minus 2. 1, 2 by 3 minus 2. So integral along OA plus integral along AB plus integral along BO equal to, first of all we got it to be equal to 1, then 2 by 3 plus 2 by 3, and then minus 2. If we simplify it, we got it equal to minus 1 by 3. That's our integral along triangle OAB, whatever be the function f1 dx plus f2 dy equal to minus 1 by 3. That's our left hand side. Let's look at the right hand side. Well done. Right hand side was also 2 minus 1 by 3. Where is it? Yeah. Integral along triangle OAB. We have done it initially, and we have applied double integral. We have uh, calculated it to be minus 1 by 3. So we get the same number both case. So left hand side of the Green's theorem equal to right hand side of the Green's theorem, and we have verified Green's theorem.